Hello everyone, we're the Stevens Advanced Robot Manipulators Lab. Our team consists of robotics researchers and students at the Stevens Institute of Technology from Hoboken, New Jersey. This is our solution to the Robothon Grand Challenge. In order to get an initial localization of the task board, we used point clouds generated by an Intel RealSense camera mounted on the end effector. We generated a source model by having the robot circle around the task board while taking scans, which we combined using post-graph optimization. We then used a ransack method to find the plane representing the table, and we filtered out the table. This left us with a source point cloud model of just the task board. At startup, we take a single scan to get a target point cloud. After filtering out the table, we perform global registration using the ransack method with FPFH features. We then refine this registration using ICP. If the fitness of the ICP registration is below a threshold, we rerun this process, which helps increase our robustness. Using the localization from the camera, we have the robot probe 2 points on the long side of the board and probe 1 point on the short side of the board. This helped adjust our localization, providing an accurate task board coordinate frame from which all other tasks are defined relative to. For pressing the button, we lower our gripper until our force sensor reading crosses a threshold, at which point we assume the button has been pressed. For the key insertion task, we probe the side of our gripper against the battery case to fine-tune our task board localization. We also use a self-centering grasp, which adjusts the robot arm while grabbing the key. This helps adjust our localization and provides for a stronger grasp. For inserting the key, the robot finds the slot by probing points in a spiral pattern. Typically, our localization is accurate enough that we only need to probe once. We then insert the key until our force sensor detects that the key is fully seated. We re-grasp the key before turning it. Finally, we drop the key to the side of the board so that it's not in the way when we pick up the Ethernet plug. We approach the task of removing the battery cover by first using a peg to slide a box across the table. We developed a hybrid force motion controller, which applies a constant downward force while traveling at a constant velocity along the table. This worked well for sliding off the battery cover using the tip of our gripper. Similar to the key, we used a self-centering grasp to pick up the Ethernet plug. We then probe points in a spiral pattern until the robot finds a spot where the plug slides in. The robot determines that the plug is sliding in if the end effector travels below a specified height with minimal force. The robot puts the plug in as far as it can until the force sensor detects either the plug or gripper hitting something. We regrasp the plug higher up and repeat this insertion step in order to ensure the plug is fully seated. Overall, our team's solution demonstrated robust techniques which could be used for robotic e-waste handling. More specifically, the algorithms used could be adapted for having a robot disassemble an item of fixed geometry. This system could be coupled with a sorting system so that each robot only sees one type of waste object. Alternatively, our system could be coupled with an object classifier, and the robot could have a database of different actions to take depending on the object. Finally, our work showed the importance of end effector design for robotic e-waste handling. For this competition, we had to design a completely new end effector because our original hand design was unable to manipulate the small taskboard items. Even with this new gripper, we were unable to remove the batteries. Handling e-waste would require a wide range of manipulation tasks, so it's necessary to either have a very adaptable end effector design or to use multiple end effectors or robots. The Stevens Advanced Robot Manipulators Lab looks forward to a future where robotics can automate the entire process for handling e-waste.